So I'm going to talk to you today about concurrency, parallelism, and coroutines. And in this case, it's about C++. We can look at the new extras in C++ 17. There's a whole bunch of parallelism stuff there, basically parallel algorithms. Then we've got two new TSs. We've got the Coroutines TS and the Concurrency TS. I'm going to talk to you about what's in those. And then I'm going to talk a bit about how coroutines work with parallel algorithms. And finally, the executors proposal, which, well, the current state of executors, because obviously there's been a long history of those. So just as an aside, all the TSs use the standard experimental namespace. This is very long for slides, so let's just assume that this using namespace alias is in effect for the whole talk, because otherwise, yeah, standard experimental on all the slides just makes all the code just that little bit longer for no extra clarity. So, parallelism in C++ 17. We have essentially a whole bunch of new overloads. The vast majority of the algorithms in the standard library have got a new overload which has a new first parameter. There's a new first parameter to the template, and the function signature has a new first parameter too. This is an execution policy. And this says the execution policy is going to tell the implementation where and how to run the steps of the algorithm. We have 3 standard provided execution policies. The first of which, standard execution partner, standard execution namespace, they're all in the standard execution namespace. We've got ACCU for sequential, which just says it's going to run the same steps in the same, essentially in the same order, one at a time, as you would get with the sequential algorithm. So it's all on the single thread that makes the call. Then probably the one that you're going to use most of the time is standard execution par, which says we're going to run all the steps of the algorithm, but on an unspecified set of threads. So, yay, multi-threading, parallelism. This is probably what you're going to use most of the time. The final one is par unseq, which is unsequenced execution of the steps on unspecified threads. And the primary motivation for this final use case, this execution policy, is the potential for vectorization. So if you're doing a very simple thing, say, incrementing integers or adding some integers or something, which you could write using the SIMD extensions, if you're actually writing it yourself as a loop, then if you use this, then if you use the par unseq execution policy, then that says to the compiler in the library, you can do this, you can vectorize things. But it's a very, very lax execution policy. So it's not that the compiler wouldn't necessarily be using its vectorization instructions. It could interleave the steps and just generally mix them up. It can start part of a step, it can suspend it, it can start another step. You can generally inline things, mix them up within the same threads as well, and migrate things across threads. It's really, really lax. So, as we'll see in a second when I go about what the thread safety implications of that are, you have to be really, really sure that your code is going to be safe for that. And so though there's a slight potential for improved performance if your code can deal with it, most of the time you're going to be using the middle one there if you're using this at all. And the sequential one is more as a debugging aid, because the code restrictions and constraints on the implementation for specifying an execution policy at all changes the way that the algorithm is specified. And so by specifying an execution policy that's sequential, then it says, well, it's all on one thread, but we now don't have quite the same constraints as the normal no execution policy overload. And then, of course, implementations might define their own. So if you've got an implementation that applies these, they might say, here's an execution policy that runs things on the GPU, or runs things as a coroutine, as you might see in a bit. So it's the potential there. The implementation can provide any extras that they like. So I said pretty much all the standard library is parallelized. It's a great big long list of all the algorithms. I don't think I missed any, but I think there's over 100. So key things that there, obviously the ones that you might expect, we've got for each, we've got transform, sort, find. In things that people are going to say is interesting, we've got transform, reduce. So that's very similar operations to the map reduce type operations that are all the rage, as it were, in the high performance computing sort of stuff. We've got nth element, which is actually a very interesting algorithm to parallelize. So having the standard library do it for you is quite good. So like I say, just about everything is there. So for the vast majority of cases where you're wanting to do simple parallelism, if you've got an embarrassingly parallel problem, then you don't have to be embarrassed about getting the standard library to do it for you. It just saves you all the work. And in use, you just add the execution policy on the front, standard execution path, and then pass in the normal set of parameters that you would for the non-parallel version. But as I said already, it's up to you to ensure that these things are thread safe, because you don't know, the standard library doesn't know what your functions do, doesn't know what the operations on your iterator is going to do. So you're saying parallelize this, and you're committing to the standard library that the operations it's going to do on your behalf are going to be okay. Yes.
To see if I understand what you're saying, I'm going to call a library function.
Yes.
I'm going to pass in a parameter, and that parameter is going to tell me just how lax the computer can be in ordering the functions in the implementation.
Yes.
For me to know what's okay, don't I, as the library author, have to document what's okay? Otherwise, if I make a change to my implementation, some client code would just break.
If you're implementing the parallel algorithms, then each of the execution policies, which I'm just about to go through, explains what it is that it requires of you. When you're calling a parallel algorithm, you pass in an execution policy. You are saying the library can now do these things, and I am guaranteeing as a person using the library that is safe. And this slide I'm just about to go through explains what those restrictions are as a library user. If you're thinking you're going to use the parallel algorithms in your library that you're writing, then yes, you need to pass on those constraints to the people using your library and say,
does the standard library say what execution policies it supports, or does it support all of them?
In the standard library, every algorithm supports all of them, plus any additional ones that the implementation provides. If the implementation provides additional ones, they need to document what those constraints are and what they might do. Yes.
How many threads or whatever are going to be used? And is there a way to limit the parallelism?
The standard provided policies do not tell you how many threads. They do not provide you a means of limiting them. Implementations might provide means where you can limit those, or say, here is a thread pool with 5 threads, use that. No, that is an implementation extension. So the standard provided ones are just these 3. They do not tell you anything about how many threads, or which threads, or any thread lifetimes or anything.
So my machine can just sit down as soon as it was.
Yes, it can sit there. No, a poor quality implementation might either not provide you. You've got a massive high performance computing environment with 1,024 cores, and it says, I'm going to run 1 thread. And that's conforming, but not very efficient. Alternatively, you've got 1 core on the desktop machine that's sitting there. It's been, it's a bit old, sitting in the cupboard, and the library says, I'm going to run 1 million threads. And, well, that's not going to be very efficient either. It's still conforming, though. So it's all quality of implementation. You're expecting the implementation to make a sensible decision for the hardware it's actually running on. So if you don't trust your library vendor to do that, choose a different vendor. Because essentially, whenever you use any C++ library, you're making that assumption that the library vendor is going to make a sensible choice for the environment that things run in. And if you can't rely on its choices, you need to look around and choose somebody else. So yeah, if you use the standard execution policies with your algorithms, then you're saying, I'm committing to it being thread safe. So what does that mean? So if you're using the sequential policy, well, you're not saying, there's no additional requirements. If you use the parallel policy, then each operation on distinct objects, you're saying, well, they're not going to have a problem with each other. You can concurrently run, if you're passing for each, doing for each, you can increment iterators. If they're different iterators, instances of iterators, even if they're copies, you can increment them safely on different threads. You can apply the for each function on different objects on different threads. But obviously, the different threads are not going to run the same function on the same object at the same time, so you don't have to worry about that. If you're using the parallel unseek, then you're not allowed to use any internal synchronization in your functions. So this is a really big restriction. So no mutexes, no atomics within the functions that you're calling. So this means that the operations really, really have to be very simple. But obviously, they're running on separate objects. So again, you're not having to worry about trying to increment the same integer twice and whether or not that's thread safe, unless separate objects in your container are going to try and do that. But you do need to, you can't use any shared state between things because that would require, unless it's completely constant for the whole operation, because that would require synchronization. And you can't use that when you're doing the unsequencing because things might be interleaved and they might be migrated across threads. So it might start the operation on one thread, suspend it, and resume it on another thread. And if you're using a mutex lock, that's undefined behavior and it's going to mess everything up. So this is the big restriction where you really, really have to know what your things are doing if you're going to try and use the parallel unsequenced execution policy. But there is potential for the implementation to squeeze that little bit of extra performance out if you've got an implementation that really knows your platform well. The initial papers for the parallel algorithms in C++ 17 allowed you to throw exceptions, and they came up with this exception list of if exceptions were thrown through multiple places, then it would gather them all together and throw one big exception, contained it all. The committee decided that this was too complicated and uncharted territory and not anything that we did anywhere else. So actually, if you throw an exception in a parallel algorithm, it just calls standard terminate. Every time. If you use one of the built-in standard library parallel execution policies. And that even applies to the sequential one. It doesn't matter whether, so this is a key way that the sequential execution policy differs from just calling the overload without an execution policy. Because if you throw an exception, it will now terminate your program rather than propagating out. Of course, an implementation is free to provide its own execution policies which have different behavior because the standard says this is determined by the execution policy and the standard execution policy is all called terminate. So a custom implementation might provide an execution policy with a different behavior, but no, these are what the standard ones do. Yes?
Is this guaranteed by checking that the function object you're going to call is no except?
No, it doesn't care whether it's no except, it cares whether it throws in practice. So, if you use a vector at, which throws if it's out of range, if all the indexes are in range, no problem. So it doesn't matter if it might throw, it's whether it does throw. If it actually throws, terminate. Yes? You can't catch the exception. Oh, so if you catch the exception internally, then yeah, it doesn't care because it doesn't leak out to the library code. So if you throw and then catch within your function, that's okay. It's only whether it leaks out. So for the vast majority of cases where you've got a simple parallel problem, then you just add the standard execution par as the first parameter, and you let the library deal with it for you. And so, yeah, you can sort execution par, begin and end. Transform with execution par, begin and end, output, and your function. And so the compiler and the library will just do it, assuming you've got a library with the parallelism stuff provided. But as ever, there is overhead. You're trying to do this because you want it to be an optimization. You've got something that you think can be parallelized abstractly. So you say to the compiler and library, go parallelize it for me. Well, there's an overhead because it's got to manage that. How do I divide up the work? Where do I put it? Which threads do I put it? How many threads am I going to spin up? It's got to do all that work. So this is not free. There is an inherent cost on all the management. So as with any optimization, you want to measure. Do the sequential one without the execution policy, and then provide the execution policy and measure on real data. See what you get. Because depends on your hardware and depends on the complexity of your task to how many processing cores you've got and things like that. So you just have to measure. You can't know a priori whether it's worth it. Okay, so next thing on the list, coroutines. We've got a technical specification for that too. So it's a technical specification, so it's not standard yet, though the Microsoft compiler does ship it and Clang has got an implementation in the works. So what is a coroutine? Well, very simply, a coroutine is a function that can be suspended mid-execution and then resumed at a later point. And when you resume it at a later point, then all the local variables from that function are going to persist with the values they had when they were suspended. So that's what we mean when we have a coroutine. And there's two fundamental types, though. There's stack-full coroutines, where it's not just the local variables, but the local variables of the parent functions all the way up the stack that are saved. And then stack-less coroutines, where it really is just this function. And the Coroutines TS says we're only dealing with stackless coroutines. When we say coroutines, we mean just this function right here. And this has advantages, because everything's localized. You've got minimal memory allocation because you don't have to worry about allocating is my stack going to be big enough to have all these things? What about if I switch coroutines, if I have many millions of coroutines in flight, do I have to worry about how full call stacks for each of these coroutines? Because that can easily add up quite a lot. And because it's localized, then the whole coroutine is just there, and all the things that are going to be saved are right there. And so, Gor Nisharov, who works at Microsoft and has worked on both that and the Clang implementation, he's got a presentation where he calls it the magic disappearing coroutines, because you write your code in the coroutines and then you compile it, and the output you can't tell because it just looks like it's a simple function, and with all the coroutine overhead has disappeared. There's no memory allocation or anything, and obviously that only works in some circumstances, but when it works, it's really good. So, by providing stackless coroutines, you can do that. With stackful coroutines, then it's much harder to make that for the compiler to make that optimization. I'm not a compiler writer, so I'm not going to comment whether it can be done, but it's definitely much harder. But there's disadvantages too. Stackless coroutines are great, but they make it harder when you're dealing with parallel algorithms, because the only thing that you can wait on in a coroutine, and if you want to if you want to suspend it, you can only because everything's local. You can only suspend the local state. You can't suspend the whole call stack because that's what we said. It's not stackful. It's local. So you suspend just the thing, just the local coroutine, and you can't. So you can't have several helper functions. You can't if your algorithm has helper functions, you can't suspend within a helper function without making it coroutines all the way down. So you have to, it changes the way that you have to design your code if you want to take advantage of this. So it's not all roses with stackless coroutines. It makes some things easy and other things hard. So it's just, this is the way that the current TS goes. I have seen proposals for stuff that allow stackful coroutines, but we're not there at the moment. So, yeah, coroutines have co-keywords. So there's 3 co-keywords. There's co-await, co-yield, and co-return. If your function has one of these in, it's a coroutine. If it's a coroutine, it must have one of these in. You cannot, for example, return with a normal return statement from inside a coroutine. If you want to put a return, you have to use co-return. And these are managed, the return type must be something that has a corresponding coroutine promise within your coroutine, because the coroutine promise is what manages how to deal with suspending and returning from your coroutine. So the expressions, you co-await, so start with co-return. Simplest coroutine is just a function that contains a co-return statement. Co-returns some value, and that returns a final value to the caller of the coroutine, just like a normal return statement. Co-await on some expression. Now this expression must be an awaitable expression. It must be something that you can wait on, and it will suspend the current coroutine until that expression is ready. Quite what that means in terms of when it's being ready is determined by what it is you're waiting for. It is very, very general. You can, for example, define an awaitable thing that will check the clock and wake up your coroutine when 10 seconds has passed, or 10 milliseconds, or whatever. Or that can be, I'm waiting for a file system operation to complete, or I'm waiting for some other function that returns a future. So it's a very, very general concept, and it all determines the type of the expression will have, it provides an awaiter, something that's awaitable, and you then have to provide overloads of various functions that determine how it waits, what it waits for, and what the resume conditions are. And then, of course, we've got co-yield. Now, this is for returning an intermediate value. So you call co-yield, it returns to the caller passing out that value. Your coroutine can then be resumed on the next line, and it can then be used. This can be used to generate a sequence of values from a single coroutine. So the coroutine promise type that's associated with the return value determines how these keywords work within your coroutine. And then so that determines how you get the return value, how the coroutine is suspended, when it's resumed, things like that. And the awaitable type determines what it is you're waiting for if you try and use a co-await. But they don't have to. Coroutines don't have to be both. You can have something that you can, within a coroutine you can await for something, and that thing doesn't have to itself be a coroutine. Alternatively, you can return something that you can't wait for. But you might well do both. It depends on the circumstances. So let's have a look at some concrete examples. Okay, so a simplest possible coroutine is something with just a co-return statement. It must return something, in this case I've chosen a future, which has a possible promise for how to evaluate how to pass the value back. But then it just always returns a single constant. So very, very simple. Alternatively, you might have something a bit more complex. Now, this is a generator. It makes 10 ints. It yields. So first time through, it will yield. It will return 0. And then you can resume the coroutine, and it will return 1, because it will carry on the loop, and I will have the same value as it did when it was suspended. And then the next time through, it will continue the loop, and so it will return 0 and 1 and 2 and 3 all the way up. It will give us 10 integers, 0 to 9. And so we have this generator type, which will have a corresponding coroutine promise that will manage how those values get out to the world. On the flip side, if we've got some function which may or may not be a coroutine that returns a future, then our coroutine can wait for the future. So we can call co-await, and at this point then the coroutine will be suspended. And that, when the future is ready, then the coroutine can be resumed, and then it can then return the result of processing that value. So yes, question at the back.
On previous slides, what will happen on the 11th call?
On the 11th call, yes. So the next time, it will resume and it will finish the function, and then your iteration is done and the coroutine is packed up. If you then try and call it again, then then that's an error. And quite what it does with that error depends on what your generator class looks like. But you would intend to use it like this. In this case, the generator class is intended to be used as a range, so it provides you with a begin and end, and you iterate through it. And then, the do stuff will be passed the integers 0 to 9. And then obviously you hit the end of the range, so you don't use it anymore. So it's up to you to just, well, I know that I'm done with that, so I'm not going to do it. But if you split out and you don't use something like the range for, then it's up to you to know when you're done, and that depends on what your class looks like. Yes?
So does it rely on picking up the error in order to find out where the end is? Because, or do you need to get that information twice?
No, well, the generator class would, no, it doesn't, it will know when it's hit the end of the loop, and so it will know that now I'm done from within the coroutine. So the overloads that you provide for dealing with the coroutine internally, you'll be able to tell, and then obviously you can make your generator class itself publish that information. So it publishes begin and end, so you can know when we get there.
So would then the range base for be the intended way to use a coroutine, or are there other ways as well? I can see how.
Well, there's many ways. So I mean, this is really, for lots of people, this is the way they will use coroutines. They will have
easiest the standard way, so there may be others. Okay.
Yeah, for lots of people, they will write essentially generators that provide a sequence of values. You use them in a coroutine. You do them like this. Obviously, the details of what you're generating. So that's a whole use case. There are other use cases, obviously. So coroutines that return futures, then it's a one-off value, but you're going to wait for it, and so you can use that with coroutines as well. We'll talk more about that in a minute. But yeah, there's lots of use cases, but this is going to be a common one. Yes, there's a question just behind you.
So you're binding us to a reference. Is it guaranteed that when we build a value, it will live as long until the next call to the coroutine?
Depends on your implementation of generator. It's entirely up to you. That's the Coroutine TS provides a framework, and it's up to you what you build with it. And if you make things that work in one way, then that's great. If they don't work like that and you make them work somewhere else, that's great too. Okay, so stackless coroutines work best if everything is a coroutine in your call stack, from the top level driving thing all the way down, because you can't suspend, you don't suspend the whole stack at any one time. I say this is particularly if you're thinking of, so it's not such an important if you're doing generators, because the generator that provides its own little capsulated thing. If you're using co-await lots in your coroutines, then it works best if the stack all the way up to the top are all coroutines, because then at every level, then you can wait for the subsequent coroutine. Because what happens when you hit a co-await within a coroutine, it returns immediately to the caller. And they've now got the handle that was returned, whatever it was. Now, in most of my examples, I use a future as the return value from the coroutine that's going to cause wait. But it can be any class that you've written that provides that. And so you return, so you call co-await, and it suspends the current coroutine and returns to the caller. Now the caller then, at some point, is going to want the value, the real return value from your coroutine. So it's going to want to wait for the value from that future. And so at this point, it's now going to wait. And for it to wait, then it needs, it needs to be a coroutine, or it's going to do a blocking call. So this works well if you can use if your implementation provides both the parallel extensions from C++17 and the Coroutines TS, then it makes sense if it can also provide a parallel as coroutine type execution policy that you can then use within your code. Because then you've got coroutines all the way down, and you can now co-await on the result of your parallel execution. And this then works within coroutines. You can then build coroutines on top of that. So that is this is an extension that I'm hoping to see in implementations as they combine both the parallel extensions from C++17 and the Coroutines TS. Okay, so leave coroutines aside for a bit, and now we'll talk about the C++ extensions for Concurrency TS. This provides a number of things. Big thing for today's talk, continuations for futures. We've also got things that are going to wait for one or all of a set of futures, or latches and barriers, which are great synchronization mechanisms, but I'm not going to talk to them about them at all in any depth today. So a latch is a one-time countdown. So you say, I've got 10 events that I want to happen, and I'm going to wait for them all to happen, and then you have the operations on your threads then say, that's done, that's done, that's done. They count down the operations. When all 10 are done, your latch is now triggered, and it stays triggered for the rest of its life. And so then any threads can wait for the latch, and it's a blocking wait until it is triggered. And obviously, if it's already triggered, then it returns immediately. So that's just it's a one-time countdown, and that's really useful for lots of things. Most common case that I use it for actually is for building multi-threaded test cases. You stick a latch at the top, and so when all the threads are in the search state ready to go, then they count down on the latch and then wait. And then when all the threads are ready, everything's ready in the right position, then the last one counts down, all the threads now go. And so so you set up your state, and you now know at this point, this is the best chance you've got of a whole set of threads being in a known state to perform your test.
Is it enough a barrier for that?
Sorry, I didn't hear that.
Enough a barrier for that?
Is it a barrier for that?
For the example you just mentioned.
Yeah, well, so the latch, it's a one-time state for setting up. A barrier is similar. The barrier class is very similar, but it's a reusable thing. So you can then so you have a set of threads, and they all wait on the barrier, and then when all of them get there, then they're all released. And then it creates a new, it resets the barrier at that point, so that now every threads have to wait again. So that's great for loops, whereas a latch is a one-time thing. So no, I use latches, like I say, for setting stuff up. When everything's ready, then we can release the latch, and it stays ready, whereas for barriers, you use it in a loop. I've got 10 threads doing various bits. I want to wait for all of them to be done before I do the final processing for this batch. Then I release the batch, and then I'm starting a new batch, and all 10 threads start their operations again. And then we repeat. So that's latches and barriers. They're great, but that's all I'm going to say today, unless people have active questions. Likewise, atomic smart pointers are in there. Atomic smart pointers are really great. These are shared pointers, but whereas with a normal shared pointer, then you have separate shared pointers that refer to the same object. You can have them on separate threads. It's all fine. The reference count is atomic. But if you've got a single shared pointer object that you wish to refer to from multiple threads and you want to change it, then you now need external synchronization. With an atomic shared pointer, you don't need external synchronization because it's an atomic operation on the object. It's a subtle distinction. It's important. It can avoid you using mutexes. It's really great, but unless anyone's got any active questions, that's all I'm going to say today. So, continuations on futures. A continuation is a new task that you want to run when whatever it is that's generating the value in the future that you're waiting for is ready. So you've got something gives you a future. Some operation gives you a future. Now I spawned an async task, and now I've got this future, and well, you can wait for it explicitly, or you can and then call something, but that blocks your current thread. Or you can then schedule a continuation, and if you schedule a continuation, then whenever that initial task is ready, it will now run my new task. And so you don't have any blocking, which is great for lots of people. You don't have any threads sitting there doing nothing, occupying whatever. You've got your task scheduled in the background. So you do this, obviously, conceptually you want to do the original task, and then you want to do the next task. And so the member function for doing this is called then. And in order to deal with exceptions, because obviously, say you've got a future of int. It might contain an int, or it might contain an exception because the original task threw. So when you call then as a continuation, well, it doesn't know whether the original future is going to hold a value or an exception. So it just passes that future into your continuation. So then you can either call, in your continuation, you want the value, you call get, and it will now give you the value, or it will throw, like if you call get under an awkward circumstance. And so that way you can then catch the exception in the continuation and deal with it there. If you don't catch it, then it then propagates out, because the then function returns a new future that holds the result of the continuation. And so the new future can then also hold an exception. So if your continuation throws, or it calls get on the past future and that throws, and it doesn't get caught, then the new future contains that exception. If you use just plain futures, then it moves in, so the source future is no longer valid. And therefore, as a consequence, only one continuation can be added. You've got some future f, you call f.then, f is no longer valid. You can't do anything else with it. You can't wait for it, you can't add a new continuation, nothing. Obviously, you can destroy it and assign new stuff, but no, that's not. It's now a different thing, so don't need to worry about that. So, code example, we've got some function, find the answer, that returns us a TS future. We've got another function processing the result that's going to take in that future. So we get our original one, we call find the answer, gives us f. We f.then and pass in process the result. It gives us a new f2 that will return. This f2 will be a future of a string because process returns a string. See, it will whatever data type you pass. So as I said about exceptions, so if you've got a fail function, it's going to return a future, but and notionally contains an int, but it's going to be already ready, and it's going to return an exceptional future that contains an exception. So if you call get on that future, it's going to throw. Well, we're not going to call get, we're going to call then, and we pass in a continuation. Now this is already ready because it's just a fixed thing, so it's going to schedule that continuation immediately on some thread. It's not specified which thread things get run on. It might be run on the current thread right here because it's already ready, or it might be run on a thread pool thread or a new thread or whatever. You don't know. The Concurrency TS actually makes it completely open. It says on an unspecified thread. Now this is a TS, so the idea is that we're going to get feedback. Implementations will try different things. People will say, we really like it when you do this, we don't like it when you do that. And hopefully then with that feedback, when we incorporate this into C++ main standard, fingers crossed, C++ 20, but no, hey, it could be later, then there will be some more guidance on that. We will have, this runs on specific threads or whatever. Anyway, so we schedule our continuation. Our continuation then calls get on the future. Our future holds an exception, it will throw, so the new f that we've got at the bottom that holds the result of our continuation now holds an exception. And then the final, in foo, then f.get will in fact throw, and it will just propagate the exception all the way out. So It just means that exceptions just keep propagating unless you actually catch them, which I think is really nice. All the examples so far, I said the continuation, it needs to take in the future, but what if you've got a function that doesn't? Well, there's two ways of doing that. The first one is that you can just wrap it in a lambda. So rather than having, this time our process result just takes a plain int. So we can't use that directly as a continuation, so you can write a lambda for your continuation, which takes in the future. You could, of course, use auto, but I'm spelling it out on the side. Takes in the continuation, takes in the future, and then calls get and passes the result into process result. Obviously, this time, if the future holds an exception, process result won't see it because the process result won't get called, because it will now propagate out. But obviously, that's your choice. You can stick a catch block in your lambda if you really care and call a different function instead, if you have an exception.
Just to be clear, the then-member function is not blocked, or is it?
Then does not block, but if the future is already ready, it might run the continuation before it returns.
Okay.
So, no. It's not specified whether it does or not. It's deliberate, in fact.
So it runs on the current
It might,
thread.
if the future is already ready, it might run it on the current thread. It might still run it on the thread pool, or a new thread or whatever. So my implementation does not run it on the current thread because I think that's undesirable, but somebody else might think that that's good behavior. So it's left unspecified. So for now, you can't rely on either way. So it's there, but it's lambdas. Some people don't like lambdas, or at least think that the overhead here clutters your code. So alternatively, is that you can write a very simple function that encapsulates that under for you. So we have this unwrapped function at the top. It takes any callable thing f that you can move into the lambda. It moves it into a new lambda and then returns that lambda. So then you can call that, our then is at the bottom line here is f.then unwrapped of process result. And that is less overhead from the point of view of the calling of the code doing it. It's essentially identical to the previous slide. But it's now encapsulated in a library function. It does also mean that whereas on the previous slide, your lambda would have to have captures if you wanted to pass any additional parameters into process result, then here, if process result was, say, a callable object that you were trying to construct with local parameters, then you can just do that directly because you're on the calling context, you're not inside a lambda, you're directly inside the function that's calling then. So, different ways. There is potential, if the implementation provides this function, then there's potential for optimizing it a little bit. But though I haven't yet worked out the best way of doing that in my library, so it doesn't do it yet. But there's potential there, if that was an implementation provided function. And certainly I've been talking to the guys who do HPX on, they were saying, oh yes, well there is potential there, and they were thinking of doing that sort of optimization too. So an interesting thing about the Concurrency TS is that async was actually pulled out of the Concurrency TS. There was originally an experimental async in there that returned an experimental future type. It actually got pulled out before it was shipped. And so there isn't an experimental async. So therefore, the only way of currently creating an experimental future is to use a promise or a package task, because there are experimental versions of those. So if you want to spawn an async task and get you an experimental future from the TS, then you're going to have to write your own thing. It's not too tricky. It fits on one slide. Spawn async function. We construct a promise to hold the return value from our future. We then get a future from that promise. Construct a new thread that's going to move the promise into that future into the thread along with the function, and we set the value on the promise so that it's ready at thread exit. And then we detach our thread, so we don't have to worry about joining it and stuff. If you actually write this, then that actually, lots of people don't like the default behavior of standard async where the futures always join in their destructor, because this doesn't. So even you could write this even if you just wanted to avoid that problem. Some people really don't like that blocking destructor, and this gets rid of that. But it does mean, by using set value at thread exit, then you wait for the thread locals to be destroyed. So it means that the thread is completely done by the time the future is ready. Which, it means that everything's tidied up nicely, and you don't then have to worry about whether there's code still running on the thread, because when you wait for the future, then that thread is now done apart from bookkeeping, as opposed to potentially running tidy up code. Okay, so we introduce continuations with standard experimental future. With experimental shared future, they work the same, except, of course, then the continuation function itself must take a shared future rather than a plain future. And as with everything on shared futures, the source remains valid, so you can then have multiple continuations on the same shared future. So you can say, when this is ready, then I want to do this, and I want to do this, and I want to do the other. You can add multiple things, and they all build on each other and work together. And again, they will schedule on unspecified threads, so they might all run concurrently, or they might run one at a time. But they will all run, and they will run when the function is ready, when the future value is ready. So just to put that in code, we've got an initial function that returns a future holding an int. And so we call find the answer, and we get call .share, so we've got a shared future out of it. And that's going to be a shared future to an int, because the original one was a future of an int. We can then schedule two more continuations. We can schedule fi.then with passing in next one, and fi.then passing in next two. So f2 and f3 are going to be a future of void and a future of int, respectively. Even though we started with a shared future, then these are going to be plain futures, because they're the direct result of a single call. There's only the one function call here that's calling next one. When you return from next one, there's only one return value. It's not immediately shared. There's only one place that can access it. So you just get a plain future to start with. But other than that, it works exactly the same as with the plain futures. Yes?
Next one and next two can be carried out in any order?
Yes. They're on unspecified threads in unspecified order, and yeah, they will happen, but you can't tell quite when, under what circumstances. Okay, so I said we got things for waiting for one or waiting for all. So when any is the one that waits for one, so you've got a whole bunch of futures. You spawned off a whole load of tasks, and you want to wait for one of them to be ready. The first one, I don't care which one it is, as soon as something's ready, I want to do something. And so that's what when any does. It comes in two overloads. There's one where you pass in explicitly, f1, f2, f3, a whole set of futures, and then it will wait for them all. And the first one that's ready, and it returns you a thing that wraps a tuple. So you pass in 5 things, you get a tuple with 5 futures in part of your result. It contains this when any result type, which also it tells you which one. It contains your tuple, and then it tells you which one of them was the one that woke you up. So you don't have to explicitly check which. Are you ready? Are you ready? Which one? No, because obviously if you've got pass in 50, then that's going to be a whole load of checks and unnecessary, because you can just know. It tells you it was 23, so you can just index through your tuple and get that value. Alternatively, you could pass in an iterative range when any. So you've got a vector of futures to start with. So you pass in when any vec.begin, vec.end, and then it returns you something that holds a vector of futures and the index of which one it was that was ready. And yes?
Why is it specifically vector and not something more generic?
Because you have to choose some container type, and vector is a good generic container type with a runtime bound rather than a, no, it could have been array, but that's got a fixed compile time bound. So, and no, it's a good default container, and so that's why it returns a vector. You don't, obviously, you can pass in anything you like, but the implementation returns a vector always. And no. Yes, so you can. So you're passing in an iterator range. So you could start with a list of futures and pass in a begin and end on your list, or no, even halfway through your list and to another point later in, and then it will return you a vector. No, because it doesn't care. It's just an iterator range, but it always gets you a vector out. So it's great for a couple of things. It's waiting for speculative tasks. So if you launched off 5 different ways of calculating pi, which one comes back first, then that's the one we'll use. As soon as something comes back, then we can take that value and then process on. In which case, then obviously you're probably going to want to cancel the ones that haven't finished, but no, that's up to you. Alternatively, then, if you're waiting for multiple steps, and you've got to process 5 things, and as soon as something's ready, I've got another thing I want to do, but I'm going to want to then come back and do the others afterwards, but I want to get started on the next step as soon as something's ready to do and give me something more to process. So you can combine that. Just to see how it looks in code, now we've got foo and bar that return futures, and then we call when any. Now actually, if these are plain futures, you're going to want to move them in, because you can't copy them. They're passed by value, so you want to move them in to make it clear that you've now passed ownership into the when any, so that then the futures that you get out in the tuple are the one and only future referencing that shared state. If they're shared futures, then that's fine, you can copy them, and they're just copies, like any other use of shared future. But the fun thing is that then, of course, it returns a future. And if everything was, it's an experimental future, because this is the part of the TS. So then you can call continuations on your result from when any. So you can say, when any of these things are ready, then do this. And that subsequent function, BAS as I've called it on the slide, is then scheduled as soon as something is ready, and you don't have to worry about blocking on the current thread. No, you just you schedule when these are ready, then go and schedule me this task, and now it will work. And you've got a new future. Obviously, I'm discarding that on the slide, but you do have a new future to represent the result of your continuation task, just like any other continuation. So that, I think, is a really powerful tool, because it allows you to aggregate results from various sources and pull them together, and then combine that with a continuation to schedule a new function to process those results. The flip side is, of course, when all. So whereas we had when any, which waits for one of a set, when all waits for all of them. And now we don't need the index to tell you which one it was, and so we just have the tuple and the vector directly wrapped in the future, rather than this when any result that wraps the tuple and an index, or the vector and an index. But otherwise, it's exactly the same. And again, so this is great for combining results of subtasks. So again, using our spawn async function we introduced on a few slides back, then we can spawn our subtasks. When they've all done, then we can get the result. You could, of course, again, use a continuation here. So it's great for composing subtasks and when you've got futures for all the results. Yes?
Can you wait, like when any, when all, on futures that return different types?
Yes.
So
yes.
what's the type that's taken into the result of when any?
Okay, so yes, so the question was, can you wait on when any, using when any with futures that return different types? Yes, you can use any mix of futures, because if you're passing them in as individual parameters, because then each parameter to your when any call can have a different type, and then it gets gathered into a tuple, which again can have different types for its elements. But if you're using a vector, the iterator version, then obviously your iterators have to have the same value type. And so then you end up with a vector containing a particular type of future, and again, each element must be identical in that case.
So if you have when any, and maybe one future returns int, and the other one returns the char,
yes.
Is the resultant future a variant of int and char?
No, because what it returns. So look, we use when all because it's on the slide, but it's the same for when any. Okay, so we've got 3 subtasks No, and they give us 3 futures, F1, F2, or 3. They can be different things, an int, a string, a double, whatever, doesn't matter. We call when any, or when all as it is on the slide. Now this gathers together, though the future returned holds a tuple of futures. And so it holds a tuple with a future of int, a future of double, and a future of string, if those were the 3 return types. So then you can then query each of the ones separately to get the values for each of the subtasks. Okay, so that was the continuations and stuff from the Concurrency TS. So one more question before we move on, yes?
So when I have a change of line, say like 5.then,
Yes.
I always have to go through the full chain, right? There's not like if I see something that happens in the first .then that could allow me an early out, I cannot get out, right? I always have to go through the full chain, or is that
Yes, yes. So the question is, if I've chained a series of then calls, so I call f, I've got my future f, and I call f.then, and then I call .then on the result from that, and .then on the result from that, then yes, it will always call each of the functions in turn. There isn't a conditional. Of course, what you could do is inside one of your continuations, you could then optionally chain additional continuations, because you've got the future back. So you call f.then, and you've got a continuation function. That original future is now passed into your continuation function. So you can now say, well, if some condition is valid, then add more continuations. Otherwise, do this. And out early. So
it's like one level of nesting.
yeah. So you can make that choice, but by default, obviously, it will just call everything because you've just passed in the continuations. Okay, so, yes, I see another question.
Do you have any plans for an observable yet?
So,
As an observable primitive, like if you see this in languages, for example, you frequently see is futures are effectively the dual to like tries, and observables are the dual for an interval, so you can consume from them constantly. From an infinite stream, you write a continuation.
so the question is plans about infinite streams of an infinite source, essentially. So you can pull from something rather than a future, which is a one-shot thing. So there are discussions about streams, and providing concurrent streams and things like that, and channels and various other names. But there's nothing that's been agreed by enough people yet. Obviously, lots of people have implementations. They say, "Oh, I really like mine," but no. Yes, so there are plans for that sort of thing, but nothing concrete that I can share with you. So we have coroutines and continuations. So they actually work quite well because futures, some of my initial slides about coroutines use the future. And that's not a mistake, and it's because futures are ideally suited for coroutines. They hold a value. You can wait on them. They can represent asynchronous tasks. So and you can create a future immediately that holds a given value. So these work really well for thinking about, the coroutine has a promise type, and it has something that you can wait for, and it just all ties in nicely with futures. And so, you can build all these things. And so you can in order to make them work concretely with coroutines, then you need to do the same things that you do with any other type. You need to provide the promise type for the coroutine. So we specialize coroutine traits to provide a promise type, and we have create a new future promise that's designed to mix with the coroutines that provides the operations necessary. And there's obviously 3 parts to that. What's it going to do? It's got to create the return object, so actually create the future that's going to be returned from our coroutine, and then specify whether to suspend before or after execution. Well, for simple examples, we're not going to want to suspend at all, either before or after, but it is possible, some circumstances with coroutines, like with the generators, you want to suspend before you're done, and you want to suspend when you're done afterwards, to make sure that everything, you don't generate any values until somebody wants one, and you don't keep running when, when you've generated the last value. So there's options like that. And then obviously you need to be able to deal with setting the value. So these are things you're going to want to provide on the coroutine promise. And there's various functions for doing that. And then on the flip side, then we want to wait for futures within a coroutine. So we need to tell it how to suspend, tell the road how to resume the coroutine, and we need to tell it what return value to provide when the coroutine is resumed. So this is when somebody calls co-await on a future. This is what we're talking about here. So whereas the previous slide was if we've got a coroutine returning a future, then we need to somehow pass the values out and deal with suspending this one. When, on the other hand, if you're trying to call co-await on a future, then you need to suspend the current coroutine. You need to be able to resume the coroutine later, and you need to obtain the value when the coroutine. So essentially, this is I need to get the return the value. So it's and again, this is a wrapper. So what we're after here, resuming the coroutine when the future is ready. So this is you want to chain a continuation, and this provides us a nice way of doing the implementation inside, because we can call chain a continuation on our future f.then resume coroutine to return the value. And again, so we need to, and this time we are overloading operator co-await, which allows us to provide a new custom awaiter that provides these operations. So we have a new future awaiter to return to wrap the future functions in a way that's palatable to the coroutine library, so that the compiler knows which functions to call. And then, when you've done that integration, then you can then have a coroutine that waits on stuff and returns values. So if we've got some coroutine, it waits on something and then returns that is a coroutine, so it uses co-return to pass value, but the output value is an experimental future. Then we can spawn some value, spawn a future, then we can use that coroutine as a continuation, because it's just a function as far as the thing's concerned. And what will happen is that it is the really nice feature of the continuations, which I didn't mention earlier, is that if the continuation function returns a future directly, then the return from the coroutine is not a future of a future. Because whereas if your continuation function returned an int, then the return from your then call is a future for an int. But if your continuation function returns a future, then you don't get a future of a future from your then call, because that's just messy. Instead, you get essentially the same future that is returned by your continuation. So if your continuation in this case returns a future of a result, then the then call at the bottom returns a future of result. So it automatically unwraps that extra layer that there would otherwise be. And so that then works really well with coroutines, because your coroutines inherently return futures as part from the coroutine, because it has to return something that's waitable later. Okay, so we're almost at the final part. We're going to talk more about coroutines and parallel algorithms. Because I mentioned earlier that the coroutines work nicely if you can, we had a parallelized coroutine potential execution policy. But let's just have a look at parallelism for a second. And so for parallelism, what we really, if we're focusing on parallelism, then what we're really wanting is to make sure that all our CPUs are doing useful stuff as much as possible. Because we don't want to have too much overhead, and we don't want to have our nice 1,000-core CPU set sitting idle. We want to be making the most of our available hardware. So blocking operations hurt, because that means that we've got a thread that's doing nothing, and the operating system has to do a nasty, expensive context switch to get a new thread to occupy that processor. So you don't want to do that. And then they complicate the scheduler as well, because you then got, well, how many threads, do I need more threads to count for the ones that are going to be blocking? So ideally, you don't want blocking threads if you're doing parallelism. Sometimes you can't avoid it, but we're trying to avoid it if we can. And coroutines provide us a means of not blocking. Because when the operation would block, when we call co-await, then rather than blocking, we suspend, and we pass the return out to the caller and say, we suspended. And so then we can schedule that using continuation type style, we can schedule that when whatever it is we're waiting for is ready, we can then resume that coroutine without any blocking anywhere. Now this is really great, because in the meantime, the current thread can then carry on doing some other tasks. So now you've got, the current thread isn't blocking, it calls a coroutine, the coroutine gets suspended, the outer calling thread then carries on. All is great. And then the coroutine itself, it was doing something, it was waiting for something. Okay, so it says, I'm suspended. When that thing's ready, then I'm going to carry on. And so then when, whatever it is, some asynchronous operation, when that is ready, then the coroutine is resumed, and that's great. The issue then comes when the outer call needed to wait for the result of that coroutine. Because if you're in a stackless coroutine, in a nested call, so we've got three functions, f calls g, calls h, calls something. H is then waiting for something, it uses co-await, it's a coroutine. So it waits a result, but whilst it's waiting, it suspends and execution resumes in g, which was the outer caller. And g then, at some point, is presumably going to wait for the result that was returned from, the final result from h. But to do so, it would have to block, because if it did it immediately, then h isn't ready yet, which is why we suspended. So it would then block. And then, obviously, f is then going to want to return from g. So we can say, okay, well, maybe g is a coroutine too. So g uses co-await rather than blocking. But then we just shunted the layer up a level. So this is why I said earlier, everything works best if everything is a coroutine. Because then, at each level, you just call co-await rather than blocking. And it all punts up to the top level. So, again, we have our low-level h, which co-awaits on some getData function, which we then process and return the result of that as a future. In the next level of g, well, we call h, and we co-await for the result from that, which we can then process and get the mid-level result, and then so on. So everything's a coroutine. And this now is non-blocking, all the way up to the top level. And then at if the top level is your parallel processing loop, then it says, oh, everything is blocked, fine. I will just stick that on the queue to be waited for and process the next task. And that's all fine. So what we really then want is we want our parallel algorithms to be implemented with coroutines. If coroutines are what we like. So we say, so if we've got some parallel function, we're passing some data, we do some form of parallel divide process that's going to divide it up into parts. In this way, in my example, I've split it into two halves, but it could be whatever. We then say, okay, well, again, we're going to recursively, divide and conquer. We're going to recursively apply our function to one half and recursively apply it to the other half, and then we're going to combine the two results. And at every level, we're assuming that we're doing parallelism if we can, and everything's a coroutine, so we say co-await everywhere, and then we co-return the final result, and we've got a future coming out. So if you're using coroutines with parallel algorithms, this is what you want to see. So this is what you would, if this parallel as coroutine execution policy that I postulated earlier, this is what you would want to see as the result of that, is that when it does the implementation, everything's a coroutine all the way down. And it then returns you something like a future which can be waited for. And obviously futures are great because you can either block on them with get, or you can co-await on them if you're in a coroutine. So, final part of the talk, we've got executors. Now, the executor proposals have had a long history. Go back to 2012, there are 19 different proposals, some of which are iterations on previous ones, so it's not 19 completely fresh proposals, but that gives you some sort of context that there has been much discussion. They were originally added to the Concurrency TS working draft before it was published, and then they got pulled out again. Part of the result, some more of these 19 papers, and had different points of view. And to be quite honest, it all boils down to what is an executor? And that's the core issue that has led to this huge amount of discussion, is that for different use cases, people mean different things. And the fundamental answer is that it's something that controls the execution of tasks, but how it controls it and what that matters to people is important, and the distinctions that people have gives rise to different questions. So, well, when you say execution of tasks, what do we mean by tasks? And there's a lot of questions around that. What kind of tasks? Are we talking just simple functions? Are we talking great big monolithic things? Are we talking any callable thing with unspecified consequences? Are we talking things that can, all sorts of, just about anything. What constraints are we imposing on what we mean by a task? Where should they run? Where should these tasks run? Should they run on a given thread? Should they run on a thread pool? Should they run on a fresh thread? Should they run on the GPU? Should they run on another processor over on another machine on the other side of the planet? Should they, all these things are important aspects to where should the task run. Are there any relationships between the tasks? Does that one have to happen before the other one? Do they share data in some fashion? Is there any synchronization between them? So can they run concurrently? Is that going to cause a problem? Or can they wait for each other? All these things. We're looking at the execution policies. We have the parallel unsequenced ones, which said you're not allowed to use any internal synchronization at all. So is that allowed? Is that is that the restriction we're going to put on tasks? Do they have to stick on the same thread? Can we move them around? If they're coroutines, can we suspend them and then resume them on another thread? Or can a given task spawn a new task? All these things are things that we need answers to. And people have different, lots of the discussion is around people who have very different opinions on which subset of answers they give to these questions. And then we have other questions about executors. Are they copyable? Are they composable? Are they abstract base types? Therefore, that you can have a pointer to a generic executor and then which you can pass through API boundaries. If you've got a task handle for some task, can you get the executor that was used to schedule it? If you're running a task currently, if you're inside a task that's running on an executor, can you get the executor that's running your current task? These are important questions. And again, people have differing opinions. But of course, we're the C++ committee, so we want all the things. We want all possible answers to all these questions. And so, the current proposal is an attempt to provide a framework that allows you, when you build an executor, to specify your set of answers to these questions. And so each individual executor will have its own set of answers. This one is a GPU executor. You can only give it tasks that will run on the GPU, and it will run its tasks on the GPU. They must therefore meet all the constraints for that. This is a thread pool executor. These tasks cannot wait for each other, but they can spawn new ones. All the different things. Now, this is a single-threaded executor. It will run the tasks you want in order you give them on a single thread. That's got a valid use case too. all these things. So the idea behind the current unified proposal is to provide that each individual executor provides its own set of constraints, but there is a framework that we can build them in. So this is the number. It's P0433R1. The R1 means it's in its second revision already. R0 is the initial revision. And it is the Unified Executors Proposal, and unified because lots of the people that worked on all the individual papers have all put their names to this one. We say, we agree. We finally come to an agreement that we can all get behind this as a unified framework. And the consequence is it then provides many, many customization points to deal with all the possible different answers to all the different questions. Well, I said we want all the answers. It doesn't quite say allow us all the things. One thing it does say is that when we say executor, it must be something that's copyable. So those people that wanted non-copyable executors now just have to pass around handles. They have to pass around a pointer or something that wraps a simple pointer to their non-copyable executor. But that's not too big a constraint. These handles, therefore, must also be equality comparable, so we can say whether you've got two handles to the same thing. Obviously, it's perfectly allowed to say they're all different. No. Compare equal? No. Always return false. And that's perfectly allowed, but you must be able to compare them. They provide a context member function, which does implementation-defined stuff. And then the core thing, to make it an executor, it must provide an execute function, where you give it some task F, and it will call execute E, F, where E is your executor, or call E.execute F. Either way round, the framework copes with either way. Then it will run your function somewhere, somehow. And obviously, the quite where and quite how is the core of why you've chosen that executor rather than another one. And the framework can then build just about everything else on top of that. But you can specialize things as you choose appropriately. So, for example, the three basic means of executing stuff. Obviously, you call execute, which may or may not block the current task because you just said execute somewhere, somehow. And where and how might be right here, right now, before I return. Or it might not. Or it might be run it right now, but not right here, and you're going to wait for it. So, no, it's allowed. Alternatively, you might post the function, queue it for execution as soon as possible, but not here, and so that I can return and carry on. And I might then post 5 things, and then at some point I expect them all to run. But on a single-threaded executor, for example, then if you post 5 things from a current task that's running on the executor, then it will wait for the current one to finish, then it will run the second one, then it will wait for that to finish, then it will run the third, and so forth. Alternatively, you might defer the execution, which is, it's a bit like that, but rather than saying don't run right now if I'm currently running a task on the executor, because this is somehow related and I want to have finished what I'm doing before you start doing the other bit. So it's preempting, it's trying to avoid blocking by saying, if you run this now, you're going to have to block and wait for me, so don't bother, just wait a bit, and then run it. So it's a bit of flexible. If your executor doesn't support all these facilities, then just don't provide the functions, and the framework will either say, I can manage that for you, that's okay, or it will say, no, I can't, so that overload now doesn't work, and people can't use that, and it will fail to compile, which at least is a hard break rather than a runtime fail. Yes?
So post fails if the executor is running the task?
If the executor can't support queuing tasks, then it will fail. If it can support queuing, then it will queue. So if you're...
So it's the same as defer.
So if it's a single-threaded executor that supports queuing, then post and defer are the same. If it's a multi-threaded one, then defer will wait until the current task is finished whereas post will spawn it, possibly run it on another thread straight away. No, so it's a subtle distinction. It took me a while to get my head around quite what was meant by the distinction when Chris was explaining it, but no, it's subtle but important sometimes. So other things you might use, we have sync execute, which is run this function f on the executor and wait until it's finished. It's a blocking call. Some people really don't like blocking, but it then allows you to return a value from your function and then use it on the following line. And if your executor is like running stuff on the GPU, then because you're running it in a separate context from the current environment, and so it allows you to run that function and then wait for it. More likely, you're probably going to be wanting to use the async versions, but these are, so there isn't an async execute, because, just for naming, but the point is that the async ones, they return you futures which can give you the result afterwards, whereas the plain post and defer and execute don't return any values. These ones will allow you to return a value from your function. So sync execute says run it on the executor and run it now and then give me the value. Async post says run it on the executor and give me a future to hold the value. And then async defer is run it on the executor and give me a future to hold the value, but don't run it right now if I'm currently running a task on the executor, like defer does on the previous slide. So again, the executor doesn't have to provide all these. The implementation, the framework can provide them for you. These ones particularly, if you've provided all three, if the executor provides all of these, then the framework can build all of these, because you can just wrap up. Someone provides a function, you can then wrap it up with a promise and to set the value to return the future. So you can provide these given the others. But if your implementation, if the executor has a more optimal way of doing it, then it can provide these itself to provide that optimization. And then there's more. There are functions to provide bulk. So I'm going to give you 100 functions to schedule on the executor all at once. And then the executor can take them all and deal with that as it sees appropriate. It can either just queue them individually, or it can use that advantage to only lock the queue once if it's got a queue with a mutex lock on it, and then just put the whole lot on the queue, or it can spawn them all at once, or whatever it feels is best. There's functions for scheduling continuations. So you've got a future f, rather than calling f dot then here's our continuation. Then you can either provide, if it's integrated in your library, you can say f dot then e for executor, comma f, to run that function on the executor when the original future is ready. Or you can, there's a free function then which does the same. So then, with an executor and a future, and then the function that you're wishing to call that will then, when that future is ready, then it will run that function as a continuation on the executor. So there's a whole bunch of additional functions there that allow for lots of customization for all the different possible use cases where you might want executors. They can also work with parallel algorithms. So you could, for example, provide an execution policy of, on some executor E, run all my functions. Whenever you're spawning new tasks, use that. And again, yes, for the continuations, you could provide an on some executor type continuation. Which, so this, again, pulls it all together. So as a programmer, then you can say, well, I really want to do this parallelism, but I know that the best way to get parallelism, actually, I'm currently running on a distributed system, and that system over there is the one that's got the best way of dealing with the parallel stuff. So I'm going to provide an executor that shifts all the work over there, but then I'm just going to call the parallel algorithm here, and then expect it to shift the work as appropriate. So it all ties together. If your implementation can provide provides all these things, then there's lots of ways of making sure they all integrate nicely. Sadly, there isn't currently any implementation that provides all these things. Visual Studio 2015 and 2017 implement the Coroutines TS. I think the 2015 one is a little bit out of date compared to the TS, but the 2017 one pretty much nails it right on, because they've written, the TS editor is Gore, who wrote the Visual Studio one. He's also working on the Clang one, and which I believe isn't quite ready yet. HPX is a library that provides parallel algorithms, and it has features which work like the Concurrency TS features with continuations and stuff. And it has some executor support, but their executors map to a different one of the older proposals and don't currently map to the new unified proposal, though you can probably get away with doing most of the same things. The customization points all look different. My Just Thread Pro library provides the Concurrency TS, and the next version, which is due out next month, is going to have support for integration with coroutines on Visual Studio and Clang if they get it finished in time before I ship that. And there's also a version with parallel algorithms coming, so there will be integration there. So there's plenty of scope in the near future for integrating all these things, but for now you've got to pick and choose which of the things do you want and make sure you pick an implementation combination that's going to provide what you want. At the end of my talk, I'll say I'm currently, the second edition of my book is now underway. You can sign up for it and you'll get the first few chapters, and you'll get subsequent chapters as they get through the publication process, and then you'll get the printed copy at the end. So that's obviously going to cover the parallel algorithms from C++ 17 and the new stuff in the Concurrency TS. So mention my library, Just Thread Pro. It's not just the Concurrency TS, it's things like actors and synchronized values and hash maps as well. So there's more to it there. It's Clang, Visual Studio, GCC. Any more questions? We've got a couple of minutes left. Yes? Two questions, go.
First one is about executors. If
Yes.
you have some sort of recursive algorithm that you want to propagate executor, then it's on the user to pass it as an argument and keep propagating, right?
Okay, so question was, if you're if you're executing a task that is recursive and you're trying to use the executive framework, then you need to pass around the executor. Yes, I mean, this is partly why the handles are supposed to be copyable, is so you can pass them around. Also, the things like the context function allow you to get a means of something else that you might pass around. I think there is also I can't remember any more details. I'd have to hunt around if there's alternatives. But yeah. Okay, second question.
Can you go back to the slide with the core weight chain?
Yes? That one.
So maybe I'm missing something, but does this allow the REST 1 and REST 2 to be executed in parallel?
Yes.
So how does it actually build a dependency graph between
Okay,
the
good. So your function starts running, and it hits. We'll call parallel divide. Now, assuming that parallel divide at some point is going to hit, it's going to spawn new tasks or something, and at some point it's going to wait for things. So at some point it will be suspended, and so then it returns a future, and we call co-await. So we're going to wait. So we say we're going to suspend the current coroutine until parallel divide is finished. In which case we then return out, and if this is called from the top level driver function, then it can say, okay, you've suspended your first coroutine, now I've got a spare thread I can run some more tasks on. So one of the things it might run is it might run one of the suspended things part of parallel divide. Okay, so, and then when that all gets finished, then when the whole parallel divide is finished, it will then resume this function. And so again, it will call down, it tries calling parallel func to calculate res1. And again, it gets suspended somehow, in which case the suspension then comes back here. And so we can then, waiting for the results. And so you've got a future, and there might be, depending on, you might find that there's better results if I skip that curl weight here, remove the curl weights from here and stuck them down here instead, then you might get better parallelism. So it depends on quite how you're structuring your code, where it's best to put the suspend points. But yeah.
If I wanted to guarantee that they can run in parallel, it would be better to have the await in the...
Yes, where you need the results, yes.
Okay, thank you.
Yes.
Kind of going back to the executor, what's the point of having the context function if that context varies based on the implementation?
Why do we need a context function if it varies on the implementation? Because sometimes you need to do implementation-specific stuff, and it's useful to be able to get that if you need it. It's like, for the standard thread class, we provide native handle. Mostly it's no use because if you're writing portable code, you can't use a native handle for anything. But if you're writing for a specific target, or you know you're using a specific executor, then you can then use the context to give you something more to hook stuff up on.
Yeah, I guess I imagine if you have some if-def blank access something with my context, then that's platform specific.
Yes, well, but it doesn't have to be platform specific. It might be library specific, or no. So there's lots more scope for that. And obviously, yeah, it depends on. It's a get me out of here, give me more access type hook. Again, in some cases it can be useful. Other cases, who cares? No, not going to use it. Any more questions? Okay, we're done. Have lunch.